So let's look at week 2 now. Done with week 1. Here's the resources. There's week 1. Let's take a look at week 2. And we have down here, we have the slides. We have the lecture outline. And then we have chapter 2. Oh, this is the one I want right here. All right. And so now we're getting into descriptive statistics. So I could go to, oh, this is super important. This is really important. When I was doing things this week, I was doing, let me see if I can find it. Hold on. I thought I put it here. Let me look for it. Okay, I found it. And this is really important. And you have a link here in the course now to my chat with Claude. And when I was chatting with Claude, I used different models. And you could choose different models here. And so here I'm on Opus 5, but I could choose Fable 5, I could choose Sonnet 5, I could choose Haiku 5. And I could do, I'm on Opus 5, but down here we have Opus 4.8, 4.7, 4.6, 3. We have Sonnet 4.6. And up here is Sonnet 5. So, and Fable 5 is the best. So I think it's going from best to worst. Best being at the top and the worst ones being at the bottom, the oldest ones being at the bottom. And when I was using Fable 5 and also Opus 5, the results were fine. The results were fine. But when I was using Haiku 4.5 and Sonnet 5, right, it was confidently telling me information that was wrong. Okay, so if you're using the AI, in our class, we have some AI exercises, some tutorials. If you're using a model and it's giving you wrong information, try a different model. And I could report that Opus 5 and Fable 5 worked fine for me at Claude. But AI might give you the wrong answers, and that's super important to know. Okay? Because if you're like, I don't get it, that doesn't make sense. And I would just switch models, and then I'd take a screenshot of what it gave me, and I'd upload it, and I'd say, hey, is the math on this correct? And switch models. And it's like, good, and I just made up a name, told it, you know, pretend like you don't know me and I'm a student, so I could do this like a student, right? And it was like when I gave it a better model to check the worst model, it caught the errors that I was noticing. Okay, get it? Makes sense? Say aye if you understand. Aye. Okay, good. All right, so now let's look at week number 2. And so here's week number 2, and here is the chapter. And what we're going to learn this week is descriptive statistics. And so I could come here and I guess I'll include it in this one because this is a lecture. And I'm using Opus 5, which is fine. What is descriptive statistics? What do you think that means just based upon hearing that phrase? Anybody? Speculate. Descriptive, like how do you describe something? How do you describe your statistics? How do you convey them in a way that's understandable? Descriptive statistics is a branch that summarizes and displays data you actually have, organizing a pile of numbers into something humans can read and understand. Frequency tables, relative frequencies, bar charts, histograms, dot plots, stem plots, shape descriptions, all of week 2 is descriptive statistics. You're taking 25 raw finishing times and turning them into one peak in the upper 20s, skewed right, a couple of slow runners past 40. That's description. Okay, inferential statistics, which you'll hit later in the course, is using a sample to draw conclusions about a population you can't fully observe, right, with a stated margin of error. And so that's inferential statistics. But right now we're looking at descriptive statistics. But there are those two ways of talking about statistics, descriptive statistics and inferential statistics. So that's good to know. And this week we focus on descriptive statistics. And so the first thing we look at are frequency tables. And frequency tables is how frequently does something occur. And so if you were to look at this person's playlist and their playlist has, by genre, they have 14 pop songs, 10 hip-hop songs, 8 rock, 5 country, and 3 other, right? The frequency out of all 40 songs, the frequency of pop is 0.35. It's 35% of the playlist, 35% of the playlist, okay? But this is the frequency table. We're listing out how much each of these categories, right, has in it. It's a frequency table. And so whatever the categories are, like give me some categories, like what fast food restaurants are there in the world? Those could be categories, right? There's McDonald's. Give me another one. In-N-Out. Give me another one. Chipotle, however you say it. Chipotle. Okay? And then we could ask, like we could put people into those categories. Where did you last eat? Which fast food restaurant was the last one you did? This one, that one, or that one? McDonald's, In-N-Out, or Chipotle. And we could count the frequency. And we could like say, okay, 12 people in this one, 14 people in that one, 18 in that one. So that's a frequency table. It's just counting stuff and putting it into categories. Makes sense, right? Not complicated. Okay. And then we can have pictures for categories, bar charts and pie charts. Okay, so here's what bar charts look like. I sometimes call these column charts because they're vertical, but bar charts could be up and down, or they could be left and right. And you saw in this penguin table, I had some charts, and this is part of the homework that you do this week. And there's a video showing you how to do it that's already in our playlist. The data lab right here, there's the video showing you how to do it. Okay. But here's a pie chart, and here are bar charts. Okay. And look at the spaces between. There's spaces between bar charts. But this shows me like the 3 different types of penguins. I had like, between 50 and 100 of this type, between 100 and 150 of this type, and just right at about 150, just a little over 150 for this type, right? But that's a bar chart. And if this was a frequency table, you could see the numbers. And then a pie chart shows portions of a whole. How many people are already familiar with this? Say aye. Okay, right? So it's not anything complicated or new. But just thinking about descriptive statistics, how do we take numbers and how do we display them? Like we saw with gapminder.org, right? How do we take numbers and how do we display them? So here, a bunch of numbers are behind this, and this is the descriptive statistics. Yeah?
I was wondering if this is going to be on YouTube right here, because I obviously
Oh, yeah.
missed something.
Yep. The video will be on YouTube.
Okay.
Yeah, so long as I'm recording, which I am.
Okay.
And then we have dot plots. And so let's say we took measurements of something and we asked people how many dollar bills do they have in their wallet. Each dot represents a person, and the number it's over is the number of dollar bills they had in their wallet. So one person had $2 in their wallet. 2 people had $3 in their wallet. 3 people had $4 in their wallet. And then here we have 1, 2, 3, 4 people had $5 in their wallet. And here we have 2 people had $6 in their wallet. 1 person had $7 in their wallet. 1 person had $8 in their wallet. And then here we have an outlier. So an outlier with data is something that is like far removed from the normal observations of data, right? So 1 person had $14 in their wallet. And there's a book actually called Outliers. And it looks at like people who are, who've done really well, who've really set themselves apart from the data. So Michael Jordan, right? He would be an outlier in basketball. He did really well. Or like Bill Gates or Elon Musk or Mark Zuckerberg. These people are outliers in terms of what they've been able to accomplish in their life. And so that's an outlier, somebody who lies outside the normal area that we're observing data. But that's a dot plot. Understand it? Say aye.
Aye.
Cool. And then we have histograms. A histogram is like if we were to take the dot plot and turn it into this, and we could ask AI, describe the difference, if I could type, describe the difference between a dot plot, describe the difference between a histogram, a bar chart, and a histogram. Because it kind of still confuses me a little bit. Bar charts for categorical data, labels with no numeric meaning, right? Right? So this many people go to McDonald's, this many people go to In-N-Out, this many people go to, what was the other one? Chipotle, right? That's a bar chart. A histogram is for quantitative data. Okay, we learned about qualitative, quantitative, categorical, numerical data. And a histogram's for quantitative data, actual numbers cut into equal width classes. And with histograms, if we put things into a category like this, if this is our raw data up here, okay, if something is between 20 and 24.9999999, it goes here. But if it's 25 to 29.99999, it goes in this one, right? And if it's 30, 30 belongs in this group. So you include the left, but you don't include the right. Left edge in, right edge out, all right? And so if these are our numbers, 21, 23, right? All these are our numbers. These would go in the first area here of the histogram. These would go in the next area here, and there should be 8 there. 1, 2, 3, 4, 5, 6, 7, 8, right? These would go, but I'm not including the 35 in this because 35 goes in that one, right? So these would be 1, 2, 3, 4, 5, 6, 7, right? These would go in that one, and then these would go in this one, and these last 2 would go in that one, okay? And notice a histogram is quantitative, numerical, right? Like these are numbers up here. And so we're like saying, okay, which numbers go into which group, which class, and how many of them are there in that group? There's 3, there's 8, there's 7, there's 5, there's 2. And so in some ways it looks like a dot plot, right? There's 4, there's 2, there's 1, there's 1.
But the dot plot, you can see it more clear.
Yeah, I like the dot plot. But you can kind of think of histogram and dot plot as the same. Let's just clarify that. Can't do a histogram and a dot plot show the same thing? And I demonstrate this with AI. One, because I didn't get, like, statistics wasn't my field of study. I don't have a PhD in it. They just gave me the book and said, here, teach this, right? And so that's one reason. It's like, okay, I want to clarify, make sure I'm explaining this correctly. But also, 2, I model for you how when you're learning something, if you're not sure about it, clarify. Be curious. Ask AI. See what kind of an answer it gives you. They're cousins, not twins. What's the same? Both display quantitative data on a number line, and both show you the shape of the distribution, where the data pile up, where there's a tail, where there are 2 peaks, whether something sits off by itself. What's different, the key thing, a dot plot keeps every individual value visible. A histogram bends values into classes and loses the individual numbers, right?
So the histogram is better at reading individual data.
The dot plot gives you the individual values, keeps them visible, right? And so that's a histogram, that's a dot plot, and a bar chart is for the categorical. You know, this category, that category. And then we have stem and leaf plot, stem and leaf display. And so if we have all these numbers, if we have all those numbers, we could say here are all the things that are in the 20s. Here are all the things that are in the 30s. Here are all the things that are in the 40s. We have the number 21. Here's the number 21. We have the number 23. See it? And then here's 23. You see it? Say aye if you see it.
Aye.
You have the number 33. 3. Here's the number 33, right? So you see how that works?
Yeah.
All right. So the cool thing about the stem and leaf display, stem and leaf plot, and the histogram, and then also the dot plot, is they start to show you the shape of your data. And you could start, and this is descriptive statistics, not inferential statistics, right? Inferential statistics is you're, observing a sample and you're making inferences about the population. Descriptive statistics is how do we take our numbers, our data, and how do we display it in a way that's easily consumable, that makes sense to us, right? We could consume it and understand it easily. And the cool thing about these descriptive statistics, the dot plot, the histogram, and the stem and leaf display, is they start to show us the shape of the data. We can see where the data is clustering, right? Like, I don't know what this data is. These are finishing times from a 5K race, right? So if you were a normal runner, if somebody said, hey, I'm a normal runner, where would you expect them probably land? Probably between 25 to 35 minutes. 15 of our measurements, we have a total of 15, 20, 22, 25. 15 out of 25 measurements are right here. So most normal runners are going to be right here, right? That's where the data is kind of heaped. If you said you're a fast runner, okay, maybe you'll be out here, or maybe you'll be here. Very few people are out here, 2 out of 25. If you said you're a slow runner, you'd probably be over here. 3 out of 25, or maybe you'd be on this lower side of, closer to 25 minutes. But this shape here starts to tell us a lot of things about our data. And there's a normal shape to a lot of data where it's kind of like this curve, where there's a big curve in the middle, the average, where most people are. There are a few people out here, really great, and a few people out down here not doing so great, whatever it is, or whatever the measurement is, right? Maybe this is like body mass index, and these are the ones doing great, and these are the ones not doing great, and here's everybody in the middle, and so that shape starts to tell us stuff. And then the shape could have different skew. So our shape could have different skew. It could be symmetric. So symmetric is like this here, right? There's look, they're all right here, right? So here's symmetric, and that's also called a bell curve, like this, okay? And do you understand that, so let's say this is height, okay? There are going to be a few people who are close to 7 feet. And there are going to be a few people who are only 4 feet, 4.5 feet when they're fully grown. But most people in here are if you're a guy, maybe 5'7", or I don't know, what's the average height for guys? Probably 5'7", right? Are you curious? I'm curious. What's the average height for men and women in America? $5'9" for men and 5'4" for women. So, right? 5'9". If this was men, right? The middle, the mean, is 5'9". And then we'd have some really tall people out here and really short people. Okay? And then we have left-skewed, and the tail tells the tail. So this is the tail. And the tail is stretching out to the left, so we call that left-skewed. Don't think everything's humped up over here, so, that's right-skewed. It's not, right? This is left-skewed. The tail tells the tail. You hear me? Do you understand what I mean when I say the tail? This is the tail. Tells the tail. Do you get it? It's kind of a weird phrase. But the tail will tell you, the tail of the shape will tell you if it's left-skewed or right-skewed. Which way is this tail pointing? To the what?
To the right. Oh, no,
the tail is pointing to the left, so this is left-skewed. Tail is pointing to the right, so this is right-skewed. And this is called bimodal. So what is this is probably like income, right? Most people aren't learning a whole bunch, and then we got a few people who are earning a ton. I don't know if that'd be income. And this one is, I have no idea. Maybe they have some examples. So we have symmetric, we have skewed right. Household incomes, skewed right. So skewed right is household income, right? So that income's a good one. And then skewed left is retirement ages. I like that, right? Here's retirement ages, skewed left. A few people retire early, most people retire later, okay? If this is age down on the x-axis. Get it? And then we have uniform, which is just flat. Every value is equally common. So the flat one would look like this. Right? Just like that. Every value is equally possible. Like maybe flight arrival times, you know, between 2 hours and 2.5 hours. And then bimodal is two distinct peaks. And so this is bimodal right there. See it? Bimodal. What else? And then we learned about outliers and then misleading graphs. Let's see if we can find a picture of a misleading graph. Misleading bar chart. Okay, this is a good one. So here, the difference between A and B looks huge, right? Like, geez, B's got a lot more. A's not doing as good, right? But this is just showing us from 36 to 50. If we see that from 0 to 50, A and B look a lot closer, don't they? So if somebody presented data like this, you'd be suspect, right? Like they're trying to paint a certain picture. They're trying to make you see it a certain way, when in reality this is visually where it's at. Do you get it? Green is at 40 here, green's at 40 here, blue's at 50 here, blue's at 50 here, you know, blue's at 50 here, blue's at 50 there, green's 40, green's 40. Same data, but this is just cut off. So it's not showing you the rest of the A's and B going all the way down to 0. And when you see that, right, it doesn't look like the difference is as big here as it does here. So that's a misleading chart. So you have to be careful and watch out for misleading charts. And that's the last thing that you learned this week. So we learned frequency, the count of data values in a category or class. Relative frequency is a category share of the whole, which is the count divided by the total. So if 10 people out of 100 like skiing, right, the relative frequency is 10%. 10 divided by 100, right? A frequency table is a table listing each category or class with its frequency and often its relative frequency. So if I do frequency table and just look at images, the value, the frequency. So the value 3 should have 2 occurrences over here. We've got 1 here and 1 here, right? So the value 4 should have 3 occurrences. We've got 1 here, 1 here, and 1 here. The value 5 should have 6 occurrences. 1, 2, 3, 4, 5, 6. The value 7 should have 1 occurrence right there. The value 8 should have 5 occurrences. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they got that wrong. But that's a frequency table. How often does something show up in the data that you're looking at? What's the count? It's a frequency table, okay? And then we have a class, a bin, or a bucket. An equal width interval of the number line used to group quantitative data includes its left edge, excludes its right. And we use that with like a histogram, touching bars over classes on a number line, the standard shape display for quantitative data. And we have a bar chart, and it's, separated bars for categories. Bar length equals the count, and a pie chart is parts of a whole, slices of one whole. And we have a dot plot, 1 dot per value stacked on a number line. And we have a stem and leaf display, right? And we remember what that looks like. Right there's the stem and leaf display. And then we also have a distribution, the overall pattern of the variables' values. And we have the shape, symmetric, skewed left, skewed right, uniform, bimodal. And we have skewed right, skewed left, and outliers, and misleading graphs. How many people feel like, cool, that's not too bad, I got it? Say aye. Great.